Welcome back to Eazy Algebra. Today we want to look at radicals and rational exponents. So a radical is something under a root. Normally we work with square roots, but there are other radicals. You can have an nth root. So the way a radical works is you have your root symbol that looks something like this. You have an index, and then you have a radicand. We'll call that r. So here n represents our index, and r represents our radicand. One way we would read this would be the nth root of r. If no index is shown, so for example, the square root of 4, we don't show a 2 here. We certainly can. When no index is shown, we assume an index of 2, the square root. So that's a very important thing to remember. All right. A rational exponent is going to relate to a square root. That's why we've thrown it in with them. If you have something like x to the 1 over n, that's going to be the same as the nth root of x. So when you have a rational exponent, the denominator is the index of your radical. So the denominator of a rational exponent is the index of the related radical. All right, let's take a look at simplifying. So to simplify a radical, if you have the radical of x times, and we'll just use a random number here, m, you can split that into the square root of x times the square root of m. And that works if these are other roots as well. So these could be nth roots. So if you have two things being multiplied under a radical, you can split them into separate radicals. That works in reverse as well. You could combine two things. And we use this when we have something like the square root of, and we'll do 6 times 4. We could rewrite that as the square root of 6 times the square root of 4, which would be the square root of 6 times 2, or 2 root 6. So we can simplify radicals using this. And the radical we didn't see that this would have come from would have been the square root of 24. So looking at the square root of 50, we ask ourselves, what is a perfect square that I can divide 50 by? Can it be divided by 4? No. Could it be divided by 16? No. By 9? No. But when we get to 25, which is 5 squared, we find that it could be rewritten as 25 times 2. And then we'll bring down 2 root 2. So now we could split that into two separate radicals. The square root of 25 times the square root of 2 minus 2 times the square root of 2. So now the square root of 25 becomes 5 square root 2 minus 2 square root 2. So if this had been a different number, we'll call it x. If you had 5 times x minus 2 times x, we would add those as like terms and say that's 3x. We'll treat square root 2 the same way because x is just representing a number and square root 2 is just a number. So we are going to do 5 minus 2 is 3 times the square root of 2. And that is our final answer for this problem. That is the simplified form. We can do the same thing if we're dealing with a rational. Here, it may or may not be practical to change it out of rational form. But what we could do is we can use some of our rules for exponents. So remember that when you have two values raised to a power, we can raise those to the power separately. And that's what we're going to do here. We're going to take x to the 3/4 and we're going to take that to the second power. We're going to take y to the 1/2 and raise that to the second power. So when we do this, we're going to multiply, because again, when you raise a power to a power, x to the n to the mth power, you multiply the powers. So we're going to multiply these. 3/4 times 2, the 2 and that 4 would cancel. So you get x to the 3/2. Y to the 1/2 times 2, again, the 2's would cancel. We get just y. So depending on the context of the problem, it might be acceptable to leave our answer like this. Or we could change this and make that y times the square root of x cubed, because 2 is our index here. And again, we don't have to show an index of 2. And 3 is our power here. There's one more concept we want to look at for this, and that is rationalizing the denominator. When you're working with radicals, you do not want a radical in the denominator of a fraction. But there's an easy way to get rid of them. Whenever you multiply a radical by itself, no matter what it is, it will get rid of the radical. Square root 2 times square root 2 would give us square root 2 squared, which will, of course, get rid of the square root, and we just have 2. So that's what we want to do in the denominator. But we can't change the value of the fraction. So if I do it to the denominator, I must do it to the numerator as well. So up here, we have to multiply by the square root of 2 as well. And here we go back to one of our earlier stated rules. Square root of x times the square root of m would be equal to the square root of x times m. So the square root of 8 times the square root of 2 would be equal to the square root of 8 times 2, or 2 square root 16. Now we can look at the square root of 16 and say, is that something we can work with? And here it turns out that not only can we work with it, it's a perfect square root. That becomes 4. So 2 times 4 over 2. We can work that out even further. 2 times 4 is 8, and 8 divided by 2 is 4. So in this instance, this problem simplified out to a whole number. That won't always be the case, but this is an example of why it's so important to rationalize the denominator. Not only is it much simpler, but in some cases, it could even be a whole number or an integer.